All right, this lecture comes with a trigger warning. We're going to do math. We're going to talk about vectors, matrices, and trigonometric functions. If you are affected in any way by those, you might consider leaving now. But don't tell me you hadn't been warned afterwards. It's computer graphics. It's the summer term in 2025 at the Bocholt campus of Westphalian University of Applied Sciences. Good day. Let's do some math. Transformation or transformations, it's plural, is the topic for today. We're going to use the blackboard. I hope you have a pencil ready and sharpened, because you might want to take notes. And yeah, let's see where this is going. We start with an easy one, translation. And the slides always work the same. We have the green, I hope it's always the green square, and we're going to move it and derive the transformation together. So this green guy with 4 vertices, V0, V1, V2, and V3, is going to be moved here. Can you think of a way of how to describe that? What do we need to do in order to move it along the magenta arrows to the final position? Okay, we first move it, let me check, slightly upwards and then to the right, or do it the other way around, move it to the right and then up. Yeah, that is one way of doing it. But then again, this would just mean you take one vector, add another vector, and then you have the result, the magenta vector. But how to apply the magenta vector, difficult to pronounce, to V0, V1, V2, and so on? We preserve the information that this is a square, so V0 is connected to V1, V1 is connected to V2, and so on. Or at least we preserve this connection in order to leave anything that is connected in the now gray original position, connected in the same way if we paint it green. So if it's just moving, the size doesn't change, the orientation doesn't change, it does not get skewed or distorted in any way. It stays a square for translation. But we need to apply the translation to V0, V1, and so on. And this would also be true if this would be a more complicated object. So anything that is made up of vertices that are connected to surfaces can be moved this way. Do you have a way that you maybe learned in maths or in physics to move stuff around? I think you were the first one. Exactly that way. That would be the most simple thing to do, or the most straightforward thing to do. You just determine this vector, let's call it t, and you might want to move it like 3 units to the right, 1 unit to the top. This is a vector that you can write down. It's 3, 1. And then you just need to add it to every vertex. And then starting with an original vertex, V1, V2, V0, and so on, you just add t to all of them, and you end up with each V dash. Okay? Because that is just the fundamental definition of a vector. That is just a direction, a movement, or an arrow between 2 points. And if you attach this arrow to one point, let's say we attach it to V0, we end up in V-0, or V0 dash, the order doesn't matter. If we fix it to V1, we end up in V1 dash. If we attach it to V2, we end up in V2 dash, and so on and so forth. And if you want to go all the way down to, I don't know the English term, it's Ortsvektoren in German, where you say a point written as a vector denotes the vector starting at the origin and ending in the point. You could still say it is this vector plus t that leads you to the translated position. It would still work that way. Okay? We'll revisit that later. Put that aside for the moment. Now we have the same square. It's again green. It's again V0 to V3, connected in the same way. And we want to make it bigger. How would we do that? We need the mic over here. We would just multiply all the points with a scalar value in order to make it bigger. Do we need to be careful with this? Yeah. Multiplying this with a scalar could leave us with nothing at all. You might want to call it, if you just multiply it by 0, there is nothing left, because that is the result of multiplying anything by 0. If you multiply this thing, the original square, with a negative number, you turn everything upside down, or left to right, and so on. It's basically mirroring it. But there's more to it. Yeah, that is true. Let's do this in 2D, and then we're gonna basically derive your answer, because I'm just not repeating it now. I'm gonna repeat it once we've derived all the stuff that went into your answer. All right. We need this setting. Let us forget about 2D for a moment, or 3D, if at all. Let's just do it in 1D. And there we take the ray of numbers where we say, okay, 0 is over here, for example. And then we take the 2, and we want to scale this number up. So let's just say x is 2, and we want to come up with an x dash. That just means, as you already said, why did I take a 2? Let's say it's a 3, because then you can more easily distinguish this from the s that I'm going to write down here. So x dash is just scaling the original x with a scalar. Let us say for the moment s is 2, then x dash is 2 times 3 equals 6, right? Does that work? No, it's a scalar. So x dash s are all scalars for the moment. It's just 1D. We're going to do 2D later. Otherwise, you could say, well, this is a vector, but still a 1D vector. But let's just do numbers for the moment. Okay? Okay. This is the single point 3 that we are scaling up by a factor of 2 in order to make it 6. Right? This does work for an object, let's say, this is our object with a side length of 3, which we scale up in the end to a side length of 6. That does work, right? We just scale one endpoint to the new location, or to the new size, and the side length changed accordingly. So this is also a factor of 2. Okay? It would be the same if we said this is 0, this is 3, this is minus 3, and we scale this one by a factor of 2 to the new location 6, this guy by a factor of 2 to the new location minus 6, and then we start with a side length of 6, and end with a side length of 12. Right? And we take a third version. This is 0. Let's say this is 1. Then this is 4. And then we scale both. The first we scale to 2, and the other one is scaled to 8, right? So we take this guy and that guy, scale it to that, scale it to there. We start from 1 to 4, and we end from 2 to 8, right? That is a 3, that is a 6 of the side length, or the length. We can remove the side because there are no sides, there are just lengths at the moment. What happened here and here that did not happen here? Yeah. Just to be clear, there is no translation involved in any of the 3. But you're absolutely right. There is a movement, or some sort of movement here, some sort of movement here. It's even more apparent here because the overlap change, or there is a shift of the intervals. Both intervals here keep their left end, but there is no movement here with respect to the center of the red line. I think the movement here is the most obvious one because even the left end shifted. But also here, the center has moved. Let's keep it that way. Why is this? Why is there a moving center in all but one case if we're scaling? And there is an infinite number of cases where the center is moving, and only a single one where the center isn't. I put it the other way around. Scaling is always in relation to the zero. So this is the only fixed point for scaling. Every other point, as you said it, moves according to the scaling. So you might say you don't only scale lengths, you also scale offsets accordingly. The left end does not have any offset. It still gets scaled, but scaling nothing leaves you at nothing. So it stays where it was. But the offset of the right end has been scaled when scaling the side length. The same is true for the offset of the end points. But since the center point does not have any offset, it does not get scaled to a different location. Okay? So just to be clear, when you are scaling a thing, and it doesn't matter what, it is always with respect to the center of the coordinate system. So this point needs to be respected as well. And if this point, the center of the object, is not located at 0, it will move. It will move according to the scaling because it has an offset to the 0 of the coordinate system, and this offset gets scaled as well. Okay? All right, so in order to scale the square from the gray to the green one, we multiply everything by a factor. But what if this guy isn't at 0? Absolutely. If this point is not located at the origin of the coordinate system, first move it there, scale, and then move the whole scaled object back. Okay? Move it to the origin. Let's say move it by 5 steps. Scale everything up, and then move it back by the inverse translation, 5 steps to the other side. Okay? Don't scale those 5 steps, because you want to move the center of the object back to where it was. Okay? Now getting back to 2D and also 3D, because we're doing 3D computer graphics and we just can depict it in 2D, but we need to apply it to 3D. How would you want to do scaling by just multiplying anything by a factor in 3D? How would that work? And let's imagine for the remainder of this lecture that this object's center is always at 0. Because if it's not, you can move it there, do your thing, and move it back. Okay? What is V0? If we're talking about 3D space. Yes, we can do it on the blackboard again. So what is V0? And we're talking about 3D, so maybe this is a cube. Am I missing this one and this one? So this is a cube, or any other 3D object. And we want to scale the object. If we know how to do it to one point, we can apply the same operation to all the other points, and the object will scale accordingly. How do you write down a 3D point? So what is V0? Yes, absolutely. That is a 3D vector. Let's maybe get rid of the 0 for the moment, because this applies to V0, V1, V100 and whatnot. So let us just say this consists of a Vx, a Vy, and a Vz. How do you scale this one? So what does it mean to say we want to know V dash, but we only have the V? How do you scale it? And now I need vector arrows, because I just can't write boldface on the blackboard. How do we scale it? By a scalar. So we could say S times V, and now to be clear, V and V dash are from a three-dimensional vector space, and S is just a number. Okay? So if you want to do that, this means just S times Vx, Vy, and Vz, and then Vx, Vy, Vz again are just numbers. And this is defined as S times Vx, S times Vy, S times Vz. Okay? Does that work? I take the cube. It's not a square anymore, it's a cube, because we're doing it in 3D. So each vertex, or corner, if you will, is a 3D vector. I can multiply this by 2 to make it bigger by a factor of 2. So if this is a cube with side lengths 1, this would lead to a cube with side lengths 2 if S is 2. Right? It's the same that we did for 1D. That does work in 3D if we write it that way. That is a boring scaling. Why not turn the cube into something, let us say, very tall, a little broad, and very thin. So not that deep. How would you do that? So it's still v dash equals something that you need to do to v, but we leave that open for the moment. And you would still want to write this down as factor times vx, factor times vy, factor times vz, but apparently there is an sx, sy, and sz in place, because otherwise you wouldn't be able to scale the x direction, the y direction, and the z direction differently. So what is the question mark? Okay, let us give this a try. So you suggest, let me write this in... No, let me just write it in white, because that is easier to get rid of, but don't copy that. So you say this would be sx, sy, sz times vx, vy, vz. How do you call this product? You know that already. That is the stuff that I have written in, I would say, STV. For S is a vector and V is a vector. So that is just the dot product. Because that means multiplying Sx and Vx plus Sy times Vy plus Sz times Vz, which is just a scalar. So, just to be clear, this does not work. Therefore, don't copy that. But there will be a multiplication involved. It just looks differently. So you're right. And you're right as to... There will be the Vx, there will be the Vy, there will be the Vz, and this is one of the reasons you learned linear algebra in math. At least you can do beautiful pictures if you are able to draw them beautifully. But you can do scaling with linear algebra. Okay, we need a two-dimensional version of a single number. How do you typically call those in mathematical terms? It looks like a 2D something of numbers. Well, I can go with a two-dimensional equivalent of a single factor, but there is a name for it. Matrix, anyone? Let's take a matrix, and that is why I go for 2D number equivalent, because there is a direction in this way, so you have a row, or let's say 3 columns in the rows. How many columns do you need, and how many rows do you need in order to do this computation, in order to get this result? So a 3D vector goes in, we multiply it on the left with a matrix, and a 3D vector goes out. The vectors are both column vectors, and we say we have a right-handed coordinate system. So this is going to be a 3 by 3 matrix. 1, 2, 3, 1, 2, 3, 1, 2, 3. And how do you multiply matrices and vectors? You've seen this already for the dot product, because I'm multiplying matrices and vectors. The one is a 1 by 3 matrix, or a row vector, and the other is a column vector, which is just a 3 by 1 matrix. But I'm still able to do matrix multiplication because I don't want to learn the dot product. Well, it's both the same. Yes, how do you multiply a matrix and a vector? You multiply the row with a column, and then you're done, basically. And you sum the products. So in order to come up with the first row of this thing, you take the first row of the matrix and multiply this with the column. We can even be more general. We need to know the first column of the vector. There is only one, but it's still the first column. And in order to get the first row in the first column, we take the first row of the matrix and the first column of the vector. And if those were matrices, you would still do the same. The third column would require the third column of this matrix, but there is only one column, but it still works. So first row in the first column, take the first row of the matrix and the first column of the other matrix. And then you just go like this. Dap, dap, dap. You multiply each element and you sum them up. So what goes here? So this is apparently a 0, because if you multiply those two, and those two, add them up, there is no Vz involved, so this needs to be 0. Is there a Vy in this row? No. 0 again. And what about this one? Yeah, that is Sx. And then you do the same thing with the other 6 guys, and you just read it from over here. Is there a Vx? No. So 0 times Vx yields 0 Vx for this row. Plus, how many times a Vy? Sy times and 0 times the Vz. And then finally, 0 times Vx plus 0 times Vy, but Sz times Vz for scaling. Okay? And coming back to you, this is just the 2D or 3D version of the single scaling factor that we used. Depicted as some 2D stuff because I need to write it down on a sheet of paper, but this is maybe just the 3D version of the scaling factor. So basically you take this matrix and this vector and you have 2D scaling. And if you take this matrix and this vector, you have the ordinary product for real numbers. There's just one number times another number, written a bit more fancy in matrix notation, but still Sx times Vx, and it works. And this also works in 128,105 million and whatnot dimensions. Just the same way. This is just a product of a matrix and another matrix, or a matrix and a vector. Okay? Good. What did I want to tell you about this one? Is there anything else? No, this is just basically three. There was one thing. This is 3 scaling factors for 3 coordinates, and you need to do it 1 factor for 1 coordinate. Therefore, you need to distribute the factors along the diagonal of the matrix. But this is just the fancy way of writing the same thing that we did for 1D for any number of dimensions, because I still want to say this is V dash equals a factor. Now it's a capital S, denoting that this is a matrix, but it's still a factor times the vertex. And that is pretty much the same that we did over here. And doing this in vector and matrix notation just saves us writing 3 lines individually, because they are all the 3 dimensions are independent of each other. So I would have to write Vx is Sx times Vx, and it's Vx dash. Apparently Vy is Sy times Vy, and Vz is Sz times Vz. So this is just a shorthand for 3 individual equations. All right? Okay. So let me just put this up for the moment while I wipe the board, because there will be more. And if you want to write the matrix, just to make clear, this is a capital boldface upright S in order to denote the matrix. And if you do lowercase upright bold, it's a vector. right. Any questions for the scaling part? Good, then let's turn this thing. Take the same square and rotate it. How would we do that? Well, the thing with the matrix worked pretty well. So why not do rotation just the same way? Why not say, okay, v dash is r times v for all the vertices. And again, careful, there is a little x on the square. If we want to rotate around the square's center, make sure the center is at the origin. Otherwise, you are rotating the whole stuff around the origin, but not the square in place. How do we rotate stuff? Well, let's say we rotate this guy into this position by an angle. Let me just check which I used. Alpha in the slides. And again, right-handed coordinate system, right-handed positive angle of rotation that way. Okay? So the axis of rotation is pointing out of the blackboard, and you take your right fingers to indicate positive rotation. How can we describe that? We start, and let us do this in 2D. We start with x and y, and we end up with x dash and y dash. How do we know x and y dash? Yes, we could use a rotation matrix, that is this one, but we should derive it in order to come up with the 9 values that go in there. Okay? Because this again is a 3 by 3 matrix that is required in order to multiply a 3D vector. So, let us say for the moment we take the 2D coordinate system, x and y, and we make it easy. We take a point here that is exactly at x equals 1, but y equals 0. Okay? And we want to rotate it, for example, to here, which means there is an angle alpha involved. How do we know the x-coordinate and the y-coordinate of this guy? How long is this one? Again, this is just a rotation, terribly drawn, but just a rotation around the origin. How long is this one? Yes. The red point over here has a distance of 1 from the origin, and if I rotate it around the origin, it still has a distance of 1. What do you know about this angle down here? If this denotes x dash. So what about the angle between the dashed line and the x-axis? Yeah, that's a 90-degree angle. Let me draw it on this side. So this is a right angle. And then maybe let us use yellow for this side and blue for the other side. All right? So blue is our x dash, if you will, and yellow is our y dash. Is there any formula, way, tool to say how large the blue one and how large the yellow one is? What does the cosine of alpha tell you? Does it tell you anything about this triangle? Just to make sure, this is a right angle, and this guy is 1. And let me just use orange for this 1 guy. So what does it tell you? It tells you the length of one side. Yes, that is true, but of which one? Well, apparently if it's not y dash, let me do it with colors. Why is it that way? Yes, it's the sine of alpha that tells you about the yellow guy. No, it's the white. No, it's not white. Why do I use white over here? This was orange. That is orange. It was white before. This is orange. So yellow over orange is the sine of alpha, and blue over orange is the cosine of alpha. Maybe to get your math in order, the co over here could be interpreted as the side co-located to the angle. Maybe. Okay, and the sine is the side at the opposite. Okay, you take the angle on one end of the triangle and you look for the other side. And the good thing is, we designed this in a way that the orange guy is 1. So we can leave it out. All right? So the cosine of alpha is blue, the sine of alpha is yellow. Okay? that correct? I think so. The sign is... yeah, that's true. So this is y dash, and that is x dash. Okay? Good. We need to draw another picture. Well, it's still the same, but now we take this point. No, it was red before. It was red before. And we rotate it over here. So this is still the orange guy. There is still a right angle over here. And there is still the angle alpha in there with a positive angle of rotation turning counterclockwise again. All right? And we want to know, once again, the blue guy and the yellow guy. This time it's the other way around. And this line is important because it separates the two. This time, the cosine of alpha is the yellow guy. Again, divided by 1, because that is set up in a way that we still have the distance 1 to the origin in this sketch. So the cosine of alpha is the yellow guy. And the blue guy is what? And once again, the yellow guy is the y dash, and the blue guy is x dash. Yes, that is minus sine of alpha. Okay? How does that help us? Especially, how does this help us if this is again x dash over 1, y dash over 1, y dash over 1, x dash over 1. Still very boring, because we don't only want to rotate this point that sits exactly at the 1, neither do we want to rotate only this point that sits exactly at y equals 1. So this is rather the original x. This is rather the original y. That is the original y. And that is the original x. Is that true? No, that is... No, that's wrong. That is the original x. And that is the original y. Because we say, in this case, that is the length of y. We set it to 1 to make things simpler. We need to divide by the orange guy. Let me just add it back in. There is the orange one. And the orange one is x for the first case and y for the other case. Okay? So we just need to somehow rearrange this. The x dash is x times... No, let me put it the other way around. Cosine alpha times x. The y dash is sine alpha x. And for this case, the y dash is cosine alpha y, and the x dash is minus sine alpha also y. Okay, this is just rearranging the equations. All right? And now let's get to one of your very first observations from today, where we moved the square, where you said you can move it first to the right and then upwards. How does this relate to these two cases? This is a multiplication, right? So there is some distributive law going on in multiplication, right? So you could say this is a vector composed of a horizontal and a vertical direction. You add the horizontal and the vertical direction up and rotate the result in order to get the overall result. You could also say, well, I factor this rotation into the sum and rotate the horizontal part, rotate the vertical part individually, add both up, both results up, and get the result. What you're doing here is you do the rotation on the horizontal part, you do the rotation on the vertical part, and now we need to sum both up. Okay? So what we take from here, from the above board, is that x dash is take the horizontal part, rotate it, so it's cosine of alpha, and add the vertical part after rotation, minus sine alpha, and the first one gets x as the factor, and the second one gets y as the factor, right? And then you do the same for y dash, which is sine of alpha times x plus cosine of alpha times y. Okay? So either take the horizontal and vertical part, add them both up and multiply the result, or take both parts individually, the horizontal and the vertical part, rotate them individually, and add them up afterwards. And that is what we do here. Okay? But now we want to go to v dash equals r times v. We again have a 3 by 3 matrix. No, I need more space. We have a 1, 2, 3, 1, 2, 3, 1, 2, 3 matrix. Multiply this by x, y, and z. And now you just need to fill in the blanks. If we want to compute, no, this is v dash, and v dash is x dash, y dash, z dash as a column vector. We want to know the first row of the result. So we just learned that we need to take the first row of the matrix and multiply it with the column of the vector and add the individual products up, right? So how many x's are in x dash? Cosine alpha, right? Cosine alpha times x goes into x dash. How many y's are in there? Minus sine alpha minus sine alpha y's, and how many z's are in there? 0. I don't see a z over there. And the same goes for y dash. I have sine alpha x's I have cosine alpha y's and 0 z's. Okay? So that is the xy plane. That is also the xy plane. What about the z's? Did it change anything? We rotated it in 2 dimensions, but we want to describe that operation, the rotation in 2 dimensions with a 3 by 3 matrix and a 3D vector. So what happened to the z's with a 2D rotation? Yes. So that is just 0, 0, 1. And you can take this 1 as the indication that that is the rotation about the z-axis. Because this 1 is either in the z row or in the z column. depending on how you want to read that. So that is the rotation about the z-axis. All right? And this block just moves around in this matrix for the other two axes. It's always cosine, sine, sine, cosine, and the only thing you need to be careful of is the location of the minus. Okay? The derivation is the same as on the board below for the rotation around the x-axis or around the y-axis. You just come up with different matrices, which you can create from those equations that you derive down here. It's again just sine and cosine. It's always this arrangement in this order, cosine, sine, sine, cosine, but the minus switches position. Okay? And we're not going to derive the y rotation or the x rotation. Just take my word for these matrices. So we did this one. That is the rotation matrix that we had. That is the rotation matrix around the x-axis. The 1 sits in the x row or x column, and it's cosine minus sine, sine, cosine. And only if you split this block for the y rotation, where the 1 needs to be in the y row or y column in order to indicate that this is the rotation around the y-axis, you need to flip the minus. But the minus on the sine. Don't introduce any minuses on the cosines. That wouldn't work. Okay? So that is the rotation. Okay? So if you missed any of the formulas, that are the transformations so far. But there is a bit more to be done. If you compare those equations on the screen, just a brief question. What is the problem? Because there is one. Or what could be the problem? What could be problematic or not as convenient as it could be? How many vertices do I need in order to create a beautiful scene with many, many detailed objects? Several thousands up to millions or even more. Okay? But transforming them is no problem because we just need to multiply the vertices with a matrix, don't we? So it's basically just, let me just switch once again. It's just basically v dash m times v. Implement this in silicon, parallelize it, and be done with it. So basically create a chip that multiplies matrices and vectors, call that GPU, plug it into your computer, and be done with it. Careful. Well, I can first rotate an object around the y-axis. Then I can rotate it around the x-axis, scale it, rotate it around the z-axis, rotate it around the x-axis, scale it, multiply all those matrices together, and apply the transformation to all the vertices of the object. And this is just a 3x3 matrix times a vector, but just parallelize it over all the vertices in the object. Okay? This doesn't work if you move the object in between, if you do a translation. Because then you have to stop, do the matrix vertex multiplication, add the translation, merge or fuse or whatever all the remaining transformations into another matrix, do the matrix vector multiplication again, stop because you somehow wanted to move the object another time, and then multiply everything again with a single matrix. So what is the problem? It's a problem with this guy, right? That is just an addition, but we have beautiful matrix multiplication for scaling and rotation. So we better find a way to do translation also as matrix times vector, because then we can first multiply all the matrices to just leave us with one, and we can do it while we are modeling the scene, if we're not doing animation. But if we're modeling the scene, we can come up with a single matrix per object, and then multiply this pretty efficiently, because we don't have to stop in order to do another addition on each vertex individually, and then do all those other stuff. Right? Good. What is that? Well, apparently this one. We did this already. But what does that mean? Because this is just a notation, a shorthand for a longer definition of this guy that you also should have seen. Because this is just a fancy form of writing numbers on top of each other and putting brackets around them. But there's a meaning to it. What does this three-tuple, if you will, mean? It carries a meaning if you say this is a vector. Well, we first need to agree on a coordinate system in which this is valid, right? So we need some notion of principal directions or fundamental directions or however you want to call them. There needs to be a notion, what does mean Vx in x direction? Where is this x direction? And then Vy for the y direction. Where is this y direction? What does that mean? And Vz, what is the z direction anyway? So this is just a shorthand for writing this. Well, and now we're entering infinite recursion because EX is again just a shorthand for 1, 0, 0 if we're in the canonical coordinate system. And then 1, 0, 0 means 1 in the direction of the x-axis of this coordinate system, and do this ad infimum. But let us stay there. This should be a definition that you have seen already somewhere, maybe in school, hopefully here. All right. This stacked notation of Vx, Vy, Vz just means move Vx steps into the direction of x, whatever this principal x direction means. Move Vy steps into the y direction, and move Vz steps into the z direction. Okay? This is just a notation using the orientation of the coordinate system. Okay? And now we are stretching math notation a little bit. It's for the math professors at our department to decide how far, but I'll give it a try. So we say Vx, Vy, Vz means Vx into the direction of Ex. Now this is a dot, plus Vy into the direction of the unit vector Ey, plus Vz into the direction of the vector Ez. Right? Where do you know where the origin of your coordinate system is? There we're talking about a coordinate system. Let us now turn it into a, I think, so-called frame of reference. Or just say, let's pin it down at a location. Where is the 0? Let's say at the location where we put the origin. And if the origin is all zeros, it doesn't matter where it is, because it doesn't change the equation, right? So we have a fourth element in this sum that is 0 in the word coordinate system or in the canonical frame of reference, because we say this is the 0 location. But let us say we define another frame of reference, maybe on the moon. This has a non-zero location in the global world frame of reference with our beautiful 0. And then again, this world frame of reference with a beautiful 0 sitting maybe at Greenwich in near London, maybe in the center of the Earth, has a non-zero position in the frame of reference of our Sun or solar system, and another non-zero location in the universe. So somehow we need to get this origin into the equation, so it might be sensible to say, yeah, the frame of reference can have an offset or an origin of which we know the location. Right? So what about saying we add a 1 here? In order to say we take the origin once, because this is a vector, the same way those are vectors, so apparently the origin doesn't fit in here, but some scalars land in the brackets. And if we now added a fourth vector, we need a factor for it. It is 1, apparently. If I can leave it out, it needs to be 1. So we put the 1 down here in order to just complete the picture. Right? And now we have something that might be interpreted as a location, because it is expressed in terms of an origin. If we leave out the origin, it is just a direction. If this is a position, and you take the difference of the difference of two positions, you get the vector, the direction between two locations. And if you do this, if you take the difference of two locations, the origin cancels out. So it gets 0. Get a 0 over here, and you get the direction that you already knew from 3D vector math. Okay? How do we translate this guy? How do we move this position now? Well, we had that already. Plus t, right? And I told you on purpose that in our canonical frame of reference, the origin is 0. So why not say, if we start at 0 and translate it to someplace else, that is the thing we want to do. We add the t. Because the other guy was 0 anyway. Right? Okay. Let's come back to matrix times vector, and now in 4 dimensions, or maybe with 4 components, because introducing the 4th element did something special to this vector space, but it still works. So we have the Vx, Vy, Vz, and the 1, that is our input vector. And we want to get out our Vx dash, Vy dash, Vz dash. And since we're still talking about locations, because that is the only thing that we can move, you can't move a vector, it does not change, because it's just a direction anywhere in space, we need to stay at 1 over here. What does this mean for the bottom row of the matrix? Well, there is no Vx. There is no Vy, there is no Vz, just the 1 that went into the equation. Okay? And this is the basis vector, 0, 0, and we need to do it in 4D. We need to add a 4th row, but this is just a direction, so this needs to be 0. Okay? This is the vector 0, 1, 0, 0. This is the vector 0, 0, 1, 0. And this could be tx, ty, tz, and we have a 1 over here, so we need a 1 there in order for it to work. By the way, we have the 1 here. That is the 1 that requires the 4th component of t to be 1. Otherwise, we wouldn't have the 1 in the sum, in this sum, because those are all zeros. Those are directions. And this is the location of the origin, therefore this needs to be 1. But we call this part t as the translation. Okay? Now, what is the matrix? If you compute this, how many Vx's are in there? Vx times, how many Vx's are in the first row? Let me put it that way. How many Vx's are in the first row? Only 1. So there needs to go the 1, multiplying the Vx, and there is no Vy and no Vz in the first row. But looking at this line, we have Vx times 1 plus Vy times 0 plus Vz times 0 plus 1 times Tx. right? So for the next row, we have 0 times Vx, 1 times Vy, so 0 times Vx, 1 times Vy, 0 times Vz, but 1 time Ty. Okay? And the same applies to the third row, where the Tz needs to go here. All right? So this 3 by 3 submatrix, if you will, this one, that is the rotation and scaling part. That one is the translation. And this row is always 0, 0, 0, 1. Unless you're doing projection. Then this needs to change because we need the fourth row for projection. All right? So basically, what you need to do is turn everything into a 4-dimensional vector. Move anything into the so-called homogeneous coordinate space, and that is not a Cartesian coordinate space, so it's not all rectangular or all orthogonal in there. Especially the fourth dimension is special. It's projective. That is why we will come back to this once we're doing projection. So you have 4D vectors with locations set to 1, directions set to 0. You need to do 4 by 4 matrices, where the top left 3 by 3 submatrix is the rotation and the scaling part, and the last column is the translation. And if you do 4 by 4 matrix times 4D vector, you magically have integrated translation into this matrix vector stuff, just by introducing the so-called homogeneous coordinates. And we have not looked into what homogeneous coordinates were. We just looked at the definition of a 3D vector and extended it by a notion, well, we need to add the displacement of the frame of reference, and ended up doing translations this way. So, to complete the picture from before, that is the set of matrices that you need. All right? Good. Now, translation, rotation. Oh, the scaling is missing. That should read scaling. Scaling and rotation as matrices, well, 4 by 4 matrices, but since they are matrices, you can multiply them together, pre-compute them per object, and do the transformation. Okay? Well, I'm going to skip a bit, because that would require to do some more math and derive it on the blackboard. We'll do it next week, because next week is hopefully short, but again, it involves math, but we come to that later. And we just go for how to apply transformations in ray tracing. So, you remember this picture, right? Good. Before we go there, any questions for the transformations? So, the 3 by 3 submatrix is just the same as we derived, this fancy 3-dimensional scaling factor, or the rotation matrix made up of, what is it, cosine minus sine, sine cosine in any distribution in the matrix, plus a fourth column with the translation. But remember, the lower right component is 1 in the matrix. All right, good. That was the picture that showed you how to compute intersections. We have a camera or a point of view from which we look into the direction of a viewing ray, hit an object, and can determine the x0 and the x1, right? But what if the blue sphere is the result of somehow transforming an original sphere from our modeling table into the scene? So basically model a sphere at the origin in our coordinate space and move it to the location of the Earth, just for example. How would you do that in ray tracing? Or would you do that in ray tracing? Would you want to do that in ray tracing? Please don't. Because intersecting a ray with a sphere is very simple if the sphere is at the origin and has unit radius, so a radius of 1. Once you move the sphere, you need to reintroduce the center of the sphere into the equation, and it just gets overly complicated. And if you scale the sphere, you need to introduce the radius. Once you scale the sphere differently in x, in y, and in z, you're not intersecting a ray and a sphere anymore. Right? So what to do instead? Any idea? Absolutely correct. We leave the sphere where it was once modeling it, but when we compute the intersections, we instead move the ray just with the inverse transformation. All right? If we just change the setting that we have over here, I'm standing here looking at you, I would perceive no change in the final result if I moved over here compared to if you moved over there. It would look the same, right? But instead of moving you over there, and the room, and the university, and the city of Bocholt, and the world, and the universe, I just decided I'd take a step to the side. Okay? Good. So we can basically do the same here in ray tracing, if we want to do that. So, we don't move the sphere from our modeling table into the scene, but we record the transformation that we want to do in order to invert it and move the camera, or maybe just the ray, with the inverse transformation. And it's just matrix multiplication, so we can invert translation, we can invert rotation, we can invert scaling. We can still multiply all of those matrices together because we know the multiplication rules for inverting a matrix product. Just change the order and invert each individual matrix. So we can compute this inverse matrix in order to transform the ray to come up with a direction dash and a P0 dash. So do this instead. Do not trace the original ray, but trace the inversely transformed ray. Come up with intersections with the original object and transform them back to their original location to do the illumination and stuff in order to make it look like you intersected the ray with a transformed sphere. Okay? But this heavily depends on the object to intersect. It might be simpler to pre-compute the transformations and apply them to triangles in your scene, and then intersect all those transformed triangles, because that is an operation that you can do pretty fast. But if it's just intersecting spheres, don't do this. All right? But fortunately, when implementing a ray tracer, you can do this decision on a per object basis. So basically, in the intersection routine of an object, you can decide to move the ray to the object, or to decide to interpret the ray as a world ray and know that you have been already transformed to world position. Okay? Good. So, we looked at translation, we looked at scaling, and we looked at rotation, and we did a very, very brief introduction to homogeneous coordinates without ever mentioning that this is homogeneous coordinates when deriving it. We just added the origin into the mix and ended up with having translation in 4D matrices. We skipped transforming the surface normals. We do this next week because we need to write some formulas on the blackboard again. And we then tied everything back into how to implement this in ray tracing and how to do this if we're intersecting spheres, which you should do for the beginning. All right. Any questions? No? Good. Then, lots of drawing on the blackboard, lots of writing fancy math symbols, lots of being lazy of writing. So instead of writing 3 equations next to each other, we just use matrices and vectors in order to simplify the notation, but mean the right thing in 3D. Yeah, that was transformations in computer graphics in the summer term of 2025 at the Bocholt campus of Westphalian University of Applied Sciences. Thanks for watching. See you next time.